Hello everyone. So we were studying about support vector machines. That's one of the important algorithm in machine learning which can perform regression and classification both. In this algorithm, as per my previous lecture, I explained we do have a hyperplane considering classification as our first problem. Hyperplane, or I would say it's a decision boundary that separates between classes. If you are having a 2D data, then a line will be a hyperplane, and if you are having a 3D data, then a plane will divide it. So if you do have n number of features, so the dimension of hyperplane will be n minus 1. That's what we have discussed in the previous class. Okay, so support vector machine do have ability to perform classification and regression both. In classification also, I told, in complex scenarios also, in complex scenarios where data points are not linearly separable, in that particular case support vector machine perform kernel trick, and it projects the data into higher dimensional so that it can classify it easily. That's a trick it apply. Linearly separable is the easy case. Non-linear separable is complicated case. For that we require kernel trick. Okay. This algorithm was first introduced in 1960, improved in 1990. It was the first algorithm at that time to beat the neural network in hand digits classification. There are many other applications of support vector machine, such as like face detection, bioinformatics, text and hypertext classification, anomaly detection, clustering, like support vector clustering (SVC). Though we say support vector machine is a supervised machine learning algorithm, okay. Uh, However, as per the working approach of SVM, here it's also mentioned clustering can be performed by it. But we are not specifically using SVM for clustering. We do use SVM for regression and classification. Okay. So these are some applications, and I also told previously what support vectors are. We do have support vector plus machine. So machine is a machine learning algorithm. Support vector are the data points which define the class boundaries, and with the help of which we can have a hyperplane. Okay, so these are the support vectors. Okay, the points which are closer to the hyperplane, and from where we are saying that class boundary is defined. So from here, green class starts, and from here, red class starts. Okay. Support vectors act as a pillar in defining the decision boundary. Okay, that's why this algorithm is said to be a support vector machine. That means a machine learning algorithm with the help of support vectors can perform regression and classification. Specifically, right now, classification we are talking about. In regression also, I will explain the logic what's used. Okay, this is a better diagram to show support vectors. Okay, so you can see the decision boundary here, and I am having red class and the blue class separated by this decision boundary, and I do have the support vectors. Not every point of data is a support vector. Only those points which are closer to the decision boundary or which are helping us in creating a decision boundary, they are called as support vectors. Okay, fine. So this is the diagram. Hyperplane, I already told you in the yesterday's class that we want a decision boundary to separate classes. That's what we are calling as a hyperplane. If we are having n dimensional data, so hyperplane will be of n minus 1 dimension. Okay, if we need to carry out binary classification, there if there is just one feature, gender, available as a feature in the dataset, then it is in one dimensional space, and a point can be used to classify. Okay, so for only one dimensional data, a point can be used to separate. In two dimensional data, a line is used to separate. In my yesterday class, everything I have explained. Okay, so all these things are written here. If you are having age and the gender, okay, no worry. Plot them on x and y axis, and you can make a line to separate between the labels. Okay, fine. So that's about hyperplane. You can see. So this is a 3D view of hyperplane. At the current, we are having 3D representation of the data. Therefore, to divide this data, I require a plane. Okay, this is 3D representation. So for 3D, I require 2D hyperplane to divide the data. Okay, fine. Now, hyperplane is simply a concept that separates n-dimensional data into groups. Okay, it's a concept, it's an approach, it's a way that how you can classify data points. Fine. In logistic regression, you have used probability. Here we are not using probability. Here you are using support vectors. Okay. That will help in defining the decision boundary. Okay. That will be your hyperplane. All right. So in machine learning terms, It is a form of a decision boundary only. There are two parts of it: negative side of the hyperplane and the positive side of the hyperplane. Okay, there are two sides, negative and positive. So we are considering hyperplane as reference. Okay, it is having positive side and negative side. Okay, we can mark like this: anything above the hyperplane is positive, anything below the hyperplane is negative. That's what we can decide. And you can see in the diagram, it's shown blue points are present on the positive side, so they are called as positive points, and red points are below, so they are called as negative points. Okay, so positive and negative sides. In hyperplane, we do have margin also. Very important, margin. I will be marking it as important, margin, because it has been told to you that support vectors are helping us to have optimal hyperplane. Yesterday also I told na, optimal decision boundary, optimal hyperplane. Support vectors are helping. Support vectors are the vectors which are closer to the decision boundary. Now, which points I will be considering support vectors? How much far I will be considering them? How much far is what it's called as margin. You can see this is my class A boundary. This is my class B boundary. So the distance between the boundaries is called as margin. Remember, this is margin. Okay, distance between class boundaries. Okay, and the support vectors are present on the class boundaries. Here are support vectors present. Okay, now you may have a question, sir. If there is any point which is present here, is it a support vector? No. Support vectors, are the points which define the decision boundary and which are present at class boundary. Okay, they are closer to the decision boundary. But you will say, sir, this point is very much closer to the decision boundary. No, I will not call it as a support vector because it will not define the decision boundary properly. Okay, I need to take care that there should be a proper distance between these two class boundaries. Those points only I will be considering to be as a support vector. And everything is hypothetical, like here. Okay, just making class boundary is a hypothetical thing. Just to use maths, just to apply maths. Okay, so this is not a support vector. This is also not a support vector. Okay, if it happens that red point will come here and green point will go there, it's a misclassification. Okay, fine. So let me share my entire screen and explain this concept thoroughly, because it's very much important to understand support vector machine and it's working. Okay. So what we have studied here is, okay, you are having two classes. So let's suppose linearly separable data only. Fine. So this is your decision boundary. Let us suppose this is your decision boundary. Here is class A, here is class B. Okay. This is the margin. Okay. Here is the margin. This one is the margin. Fine. Whatever be the points present here, that will be class A points, they are called as support vectors. These are class B points, they are called as support vectors. Okay, they are not. Fine. It's called as hyperplane. Okay, hyperplane, which is a line or a decision boundary. So decision boundary is a hyperplane. Okay. Then I told margin M. Okay, this is margin M. Width. Okay, M defines width between the class boundaries. Okay, let us suppose D is the distance between class A and class B. D is the distance. Okay, fine, we can put it. No worries. Okay, so mark it as D. So this will be D by 2. This will be D by 2. D by 2, D by 2. Okay, for simplicity, we are taking each and everything. Okay, fine. Now, we have also been told that anything below the hyperplane or decision boundary is negative. Anything above the decision boundary or hyperplane is positive. Okay, fine. Now, so linearly separable. No, no, right now we are dealing with the case linearly separable. With this only, we have to perform the derivation, linearly separable. We have to consider the easiest case. This will be used to perform the entire mathematical concept of support vector machine. Okay. In general, how we write linear equation? You know, y equal to mx plus b. Okay, this is how you write y equal to mx plus b. Okay, then I'm just hoping that this is the equation of a line mx plus b. Then what I can do is, can I bring y here? So it will be like mx plus b minus y equal to 0. Okay, mx plus b minus y equal to 0. Then what else I can do here? I haven't been told further is any reorganization of the terms can be made. So just keep this thing in your mind. I will get back to it. Okay. Before that, margin, which you are calling as width between the classes, class boundaries. We are having two kind of margin, soft margin and hard margin. Two kind of margins are there, soft and hard. Okay, I will be talking about them, soft margin and the hard margin. Hard margin is a type of margin which is used in linearly separable data. It is very rigid in classification, hence can result in overfitting. That means very rigid. Here you can see hard margin. Hard margin is clearly classifying the data points. You can see this line is clearly classifying the data points. Okay, that means here you are getting 100% accuracy of classification. So you have made a margin that is clearly classifying the data points, which is rigid in nature. That's what you are calling it as hard margin. But there is one thing mentioned, overfitting. Whenever you get 100% accuracy, overfitting is something which come up automatically, because real world data is not like so easy that you can divide it with a hard margin and you can get 100% accuracy. Most of our data is complex. So we do have soft margin also. Soft margin is a margin where you are allowing mistakes, where you are allowing misclassification also, but not so much minimum. Here you can see the blue point came into the hyperplane. Okay, this region. Red point also came here. Some of the blue point crossed the boundary. Misclassification. This is also misclassification. Okay. So this is a kind of scenario which has been mostly present in the data. We have to make a margin. We have to make a decision boundary. But we have to tolerate some mistakes. Not much. See, again, come to your goal. Your goal is to find optimal hyperplane. Okay, that's what your goal is. A hyperplane which can separate the data points in a best way. Okay, and your classes should look clear. Okay, this is A, this is B. That hyperplane, that decision boundary I need. Fine. So we start our algorithm. Okay, and it starts building the decision boundary. And decision boundary it makes It tried to increase margin. Okay, it tried to increase margin. That means if this is a descent boundary, it try to increase margin. The margin should have to be more. Therefore, class A and class B should clearly looks separated. If my margin is less, okay, if my margin is less, then class A and class B are closer. And if margin is more, class A and class B are clearly separated. My goal is to find optimal, neither max, neither min. Optimal. That should clearly help us in understanding that this point is of class A, this point is of class B. That's what you have to make. A decision boundary. So, when you start making decision boundary, in order to achieve optimal hyperplane, you may face such kind of scenario, soft margin, where you have to afford some misclassifications also. But there is a limit, no? If you keep on increasing the margin, see, I want to increase the margin. I want to increase the margin so that I can clearly classify A and B. But increasing the margin can result into misclassification. So again, I need to decrease it. Whenever the misclassification goes on increasing, then I need to take a step, decrease the size of the margin to prevent misclassification. See, some misclassification I can afford. That's not an issue. But if the misclassification goes on increasing, then it's not affordable. Okay. So accordingly, I need to take step. Okay. That is what it's called as an optimal hyperplane. And it has been told that for the maths of machine learning, I need max margin. Margin should have to be maximum. Okay. That's what been told in support vector machine. Okay. Now, how to do this thing and how to turn up all the concepts into maths. See, here it is. Maximum margin hyperplane. The primary objective of SVM is to find optimal hyperplane where data points are efficiently classified with fewer errors as possible. See, error can be there, misclassification can be there, but few. Few mistakes I can afford, but not more. So the maximum margin hyperplane is a hyperplane drawn that gives largest margin, which can be used for classification. Okay, so here you can see in the diagram. I have explained in the previous class also. We are having three hyperplanes: H1, H2, H3. If the question came to you, which one is optimal hyperplane? You will say, sir, H1 we are rejecting. Why? Sir, ये तो misclassification है. This hyperplane is misclassifying. These black points are coming in red in the white region. H2 is okay. It is correctly classifying black from white. So it is okay. But it is not optimal. It is okay but not optimal. H3 is optimal. Why? Because this is your boundary for black, this is the boundary for white, and this is the margin. Okay, this is your margin, and here I am getting max margin among H1, H2, and H3. Here I am getting the maximum margin. So, a decision boundary or hyperplane where you are getting the maximum margin, you have to select that. And how it's decided? With the help of support vector. This is support vector, this is support vector, this is support vector. These support vectors will form class boundaries, and accordingly, my decision boundary will be made. This will be the margin. Margin should have to be max. Got it? Okay. So, remember, you may be asked a question: what is the difference between hard margin and soft margin? You should know it. Okay. Kernel trick. Well, the kernel trick, as I explained, we are not going in today's class in detail, but I told when you are having complex data distribution, that means the classes are intermixed. In that, SVM use kernel trick to classify non-linearly separable data. A data which cannot be separated by a line, that is said to be non-linearly separable. Okay, not by a line. Okay, you can see above. This is non-linearly separable. Okay, this is linearly separable. This is non-linearly separable. So for non-linearly separable, I have to do something. Then I can classify red from blue. Don't think that, sir, can we make like this, sir? No, it's just a representation that your data is non-linearly separable. It's just a representation. Got it? In order to separate my model, my support vector machine will perform or use kernel trick. Okay, and I told in the kernel trick what it do. It transform data to higher dimension. How? Let's see what happens in a kernel trick. See, we have to represent the data in a higher dimension. For example, a 1D data can be represented in 2D, 2D can be represented in 3D, and so on. So, why it is called as kernel trick? See, SVM cleverly represents nonlinear data using any of the kernel function. There are kernel functions. Okay, there are some functions which we call them as a kernel functions. So SVM uses these kernel functions as a kernel trick. The reality is the data points still remain the same. They have not actually been transformed, but they looks like that they have been transformed just to show classification. That is why it is called kernel trick. So it's hypothetically done by SVM. that it will transform the data to higher dimension. It will put the data, it will represent the data in higher dimension, and then it will classify. Okay, fine. So here you can see one dimensional linearly inseparable class. Here it is. It is inseparable because I can't separate this red and the blue with a line. So it applied kernel trick. That means it introduced the data points, it represent the data points on polynomial of degree 2. Okay. So here when I represent this point on a polynomial, these are blue points, these are blue points, these are red points. Now I can separate blue from red. So transformed with polynomial kernel of degree 2. I do have this polynomial kernel. I am having that. I am having many kernels available in SVM that can represent data on higher dimension. Okay, so from 1D to 2D. Okay, how you will classify this problem? What you will do? This is 2D, and you can see blue are in center, and all these red are surrounding it. This is also linearly inseparable, complex of the complex case. You cannot separate these two, but we are having a kernel trick. This is 2D na. I can make 3D. Okay, what I can do is I can make 3D. So this 2D can be transformed to 3D, and whatever your blue points which are inside can be projected on third axis. So red points are in xy and blue points are in z. Okay, so I can make a plane which can classify red and blue. Okay, so again, to perform this thing also kernel trick is required. You can see that SVM works in a very challenging mode. Okay, so far what we have learned? We have learned that okay, the theme of support vector machine is to classify, okay, classify data. We are using classification here. For that, it said there are two cases: linearly separable, non linearly separable. Linearly separable is the basic case. For non linear, I need to use kernel trick to classify. Okay. Overall concept of support vector machine says that you have to find optimal decision boundary. Okay, that is required. You want a hyperplane that is having, okay, max margin. Okay, margin should be maximum. That means distance between the class boundaries, this should be maximum. I want to solve my equation, my support vector equation on this concept only, max margin. So we'll increase the margin In this case, you may have misclassification. You keep on increasing the margin, but if the misclassification increases, don't do this more. Reduce the margin. So anyhow, I need to do the adjustment between max and min. See, if you make a min, then margin width is very less. If this is your class boundary, okay, this is a class boundary for A, this is for B. See, the margin is very low. That's what we don't want. We want max margin. Minimum margin doesn't give you, it's underfitting, like, okay, it's underfitting, maybe, okay. In maximum, if there are misclassification, then also you may face such an issue. We have to pick up each and every corner where it could be an underfitting, where it could be an overfitting. See, maximum, if you have many misclassification, many misclassification, then it's underfitting. Okay, how many misclassifications can be there? How? That means if the red points are present here, here also. This is red points. Some red points are here. Some blue points are here. This is the blue margin. So you decided to reduce the margin. Okay, and reducing the margin will not be an appropriate case. Okay, so I need to be somewhere between max and min, optimal. Fine. Kernel trick, you have seen, and there are many kernel tricks like polynomial kernel function we are having, which can have a degree 2, 3, etc. We are having RBF also, radial basis function. This function behaves as a weighted nearest neighbor model, RBF. Okay, RBF, radial basis function. It behaves as weighted nearest neighbor model. It transforms data by representing in infinite dimensions. Then using the weighted nearest neighbor for classification. Okay, so this is radial basis. By default in SVM we do have RBF only for classification. By default RBF. This is sigmoid. This is linearly separable, easy case. This is polynomial, 2 degree, 3 degree. This is RBF, this is sigmoid. And here are the equations. For linear, we can have this equation. For polynomial, we are having this equation. That means linear to the power degree. And this is Gaussian or RBF. Okay. So e key power minus, okay, e key exponential, no? E key power minus x square by 2 sigma square. This is Gaussian, RBF. Okay, got it. So radial basis kernel, that means the formula represents above is the Gaussian RBF. For Gaussian, you very well know the formula. 1 upon square root of 2 pi sigma e की power minus x minus nu का square upon 2 sigma square. This is Gaussian distribution formula. So RBF based upon this. There is one more parameter C. This is regularization parameter, and we have seen this parameter in logistic regression also. To control, okay, if your model is overfitting, then you are going to add penalty. How much penalty you have to impose depends upon C. because C is inverse of penalty. If C is more, penalty is less. If penalty is more, C is less. We have seen this concept in logistic regression. Okay, got it. So that's about hard margin, short margin, kernel trick. I have just given you an idea. But when you come to maths, this is more complicated. I will be talking about maths. So far, I haven't discussed about maths. I just gave you one equation, mx plus b minus y equal to 0. Just this thing only I gave. Okay, we have to compare it with wx plus b. That's what we have to do. Wx plus b. We have to compare it. And how this comparison will be made? Okay, you are having mx minus y plus b equal to 0. You can write mx then plus minus 1 y plus b equal to 0. Okay, and then here I can write m minus 1 and x and y. M minus 1 and x and y. How? Because I will be representing this in form of vectors, dot product of vectors. Okay, so I will let you know ahead in my the next lectures. Okay, where I will be doing the entire maths. However, in the next class I will take a short intro about this thing, what I taught in today's class, and then I will proceed towards the derivation. Very much important again. You have to be there. Okay, fine. So that's all for today's class. Let me stop presenting.